that you will be performing two different experiments. These are two altogether different experiments. Measurement of Stefan's constant and measurement of high resistance by decay. In fact, we discussed about steady state. In steady state, we have to wait for 45 minutes. So now the question is, what will you do in those 45 minutes? So to just take care of those 45 minutes, we have another experiment for you, and that is measurement of high resistance by decay. So that is how basically we can take care of the time. Okay, so we will begin with the first experiment first, and then we will move to the second experiment. So you all know about energy radiated by a body. If you heat a body, it will radiate heat. Okay, so energy radiated by a body depends upon its surface area, it depends upon the absolute temperature, and it depends upon the nature of a body, and we call this one here emissivity. Emissivity is defined as the ratio of energy radiated per unit area of a given surface to the energy radiated per unit area of a perfectly black body when both the bodies are at the same temperature. This is definition of small p. For a black body, the value of small p is 1, as in reality there is no body which has the value of E to be equal to 1, E is always less than 1. Okay, this is the well-known Stefan's law. The value of heat radiated here. Okay, this is given per second. It is sigma, Stefan's constant, epsilon, emissivity, A, area cross section, and temperature T to the power of 4. The value of sigma is given by this formula if you derive either thermodynamically or by statistical methods. Okay, so but the well-known law is Q is equal to sigma T to the power 4. Now again, the heat transfer from a body can happen by these three mechanisms: conduction, convection, and radiation. If we want to measure sigma, Stefan's constant, it is essential for the radiation to dominate the heat transfer, and we have to get rid of basically the conduction and convection. So this can be achieved by the following steps. One, we can blacken the surface of a body and that of an enclosure to make epsilon have a maximum value of nearly unity, not equal to unity. Okay, secondly, we can by increasing the resistance to heat conduction by using very thin wires for electrical measurements and by using a nylon thread of poor conductivity to suspend the sample. Okay, we are using thin wire. Thin wires will have larger resistance. Okay, RA over L. R is equal to rho into L over A. So lesser the thickness, more will be the resistance, and by using a nylon thread, not metallic thread, because metallic thread the heat will be lost by conduction. Okay, so we are hanging the whole system. We will show you. Okay, here we will discuss about this. So we are using a nylon thread to suspend, in fact, the sample so that we can get rid of this conduction and convection. And then using a closed enclosure to reduce convection losses due to the currents of air. We will not allow the sample to let the air take away the heat from the sample. Okay, so we have to enclose it properly. The formula is Q is equal to this one, but if the temperature of the surrounding is T1, then we can rewrite the formula for Q. Q is equal to sigma into epsilon into A, T2 to the power 4 minus T1 to the power 4. T2 is the temperature of a body and T1 is the temperature of the surroundings. Okay, so this is the formula which is used for measuring epsilon. What we should be able to estimate the value of Q. And if T2 is measured, then we can find out the value of sigma, because A and epsilon, A is known, A is the area of a sample, and epsilon we can basically make it to 1, okay, or close to 1. So this is the schematic diagram of the experiment. Okay, this is how, in fact, this is all inside this box. So I will tell you the things. Here we take a aluminum cylinder, 3 cm long, 2 cm outer diameter, and 0.5 mm wall thickness. In fact, none of these tube lights. You must have seen the small starter of the tube light made up of aluminum. The same starter has been taken for this. The same starter. So the starter is made up of aluminum. So it's an aluminum cylinder. Length is 3 cm long, 2 cm outer diameter, and the wall thickness is 0.5 millimeter. This is our sample. Okay, heater here is made this way. Okay, heater is made by a Teflon cylinder. So we take a Teflon cylinder of outer diameter 10 millimeter, thickness 0.5 millimeter, and length 2.5 centimeter. What we do, we have basically a Teflon cylinder. Okay, so we drill holes onto the circumference of this Teflon, 5 holes equidistant from each other. Okay, if you view me this copy, I can show you. You have basically a Teflon like this, so you just roll it. So this is our cylinder. So now you drill 5 holes, one here, one here, one here, one here. So 5 holes here and 5 holes here. Okay, now you take 5 resistors of 120 ohm, 100 ohm and quarter watt. Okay, so one end is inserted here, other end is inserted here. So we have basically the one resistor here, another resistor here. So we have 5 resistors equidistant lying onto the surface of the Teflon cylinder. Now inner wires, the one connected, so we twist them together, and the lower one is also twisted together. So we have basically, thank you. So we have 100 ohm quarter watt resistances connected in parallel, and they are 5 in number. They are connected in parallel. So 1 by 100 plus 1 by 100, 5 by 100. So effective resistance of the heater is 20 ohm. So our heater is made up of a Teflon cylinder using 5 resistors, and the effective resistance is 20 ohm. Okay. So then what we do? We put this Teflon cylinder inside our aluminum cylinder. So this is a heater, and between these two we fill it with aluminum foil so that there is a proper contact, with thermal contact between the aluminum cylinder and the heater. Okay, now after this, so this is our system. So we now blacken this outer cylinder by using the black paint. Okay, here this is coated with painted black, and emissivity of painted black is reported to lie between 0.9 to 0.95. So we paint it, and then we suspend this by using a nylon thread from the top of a steel cylinder like this. So it is all inside, it's hanging. Okay, and the inner surface of this steel cylinder is also coated. This is also coated black. Okay, before doing this, we have basically the 2 terminals here from the aluminum cylinder. We take it, we connect a copper constant thermocouple, because we have to measure the temperature and we have to allow the heat to pass through so that we can heat the sample. Here on this, you basically have 3 terminals. One is for the heater. So these 2 terminals are for the heater, and this is the RCA socket for the thermocouple. Okay, so inside you have to heat the sample and you have to measure the temperature of a sample by using a copper constant thermocouple. So that is what you see on the top of this box. Okay, then after this, so this is how your box looks like. Okay, the same thing. This is thermocouple, RCA socket, and these 2 are heater leads. Then we connect the 2 thermocouple leads. The output of a thermocouple is connected to one of the 3 terminals, 3 possibilities of a DC differential amplifier. We select amplification factor of 100, and the amplified output is measured by a digital multimeter. This is a constant current source. We connect the 2 ends of a constant current source to the heater, and we can set the current. Okay, so heat is carried by a current source, that is Joule heating. So Q is equal to I square R. I is our choice. R is the resistance of a heater, that is 20 ohm in our case. I is the current. So from thermocouple output, we can find out the value of T2 minus T1 to be equal to V corrected. V corrected is V plus minus V minus. You already know the theory of DC difference amplifier. We have to measure the voltage. Okay, first of all, we have to set the offset to 0. The 2 terminals has to be sorted, and then we minimize the offset. Then we connect the thermocouple ends to one of the 2, either to I1 or to I2 or to I3. we select it properly onto the panel of a DC differential amplifier. So we measure B1 plus and B1 minus. Okay, we just subtract them from each other and divide it by 2. So that is B corrected. There should be a minus sign here. Okay, and P2 minus P1 can be obtained by using this B corrected to be divided by alpha. Alpha is basically 40 microvolt per Kelvin. This is thermoelectric power of copper transcendental thermocouple. We use this value yesterday also. Okay, and mu is 100. So we can find out that T1 is the room temperature that we can measure by mercury thermometer, and we can make use of this formula to find out T2. The surface area of the cylinder can be obtained by the well-known formula. A is equal to 2 pi r into r plus rl. R is the radius and L is the length of a cylinder. Under steady state conditions, now for every current we have to wait for 45 minutes till steady state is reached. So in steady state, the value of Q is equal to epsilon rho sigma epsilon A T2 to the power 4 minus T1 to the power 4. What we do now, after we record the value of T2 through DC differential amplifier for several currents, then we plot a graph between T2 to the power 4 minus T1 to the power 4 and read the slope of the curve, slope of the straight line gives us the value of this difference constant. This is again the experimental procedure. Okay, we have to connect the banana terminals to the heater through constant current source. The current that we have to set is 200 milliampere. Then DC differential amplifier terminal I1 to RCA socket of the thermocouple on the box. We have to choose the amplification factor of 100. We have to take now a digital multimeter in 200 millivolts range. We have to connect it to the output of a DC differential amplifier. We have to wait till thermo EMF shown by TMM reaches a steady value. It is about 1 hour, but you have to wait for 40-45 minutes till this becomes constant. Then we have to reverse the terminal on DC differential amplifier to find out the negative values also. And then after this, we have to reduce the current in the step of 20 milliampere till 100. So we have to start from 200, 200, 180, 160, 140, 120 and 100. We have to take 5-6 reading. We have to wait for 45 minutes till steady state is reached. Okay, and in the meantime, you have to do the other experiment that I will discuss just after this. These are the readings. Here the room temperature is 299 degree Kelvin. Okay, 26 degree centigrade. Diameter of a cylinder. This is the area. The resistance of a heater is 20.1 ohm. So you have this is the current. Okay, this Q is I square into R. R is known, so we can find out this one. This positive value and the negative value can be obtained by DC differential amplifier. We find out the corrected value. Okay, corrected value is B plus minus B minus divided by 2. We convert it into difference of temperature by dividing this by 4. Okay, that is 40 microvolt per degree Kelvin. This is the thermal capacity of a copper transcendental thermocouple. T1 is known, so we find out the value of T2. Then we calculate T2 to the power 4 minus T1 to the power 4. Finally, we plot a graph between Q and T2 to the power 4 minus T1 to the power of 4. Okay, and the slope gives us the value of sigma. Okay, here there are two slides on design control parameter, that why we take a cylinder of aluminum having a very less mass, why a small cylinder is needed. Okay, so normally in heat experiment what happens is, okay, we ask our students to take, let us say, 5 observations, and 5 observations has to be taken in 3 hours. So we talk about this, that how can we force our student, or how can we help our student to take 5 readings over a stipulated time of 2.5 hours or 3 hours. So temperature rises from the initial room temperature to the final room temperature like this. Theta T is theta infinity 1 minus e to the power minus t over tau. It is similar to the charging of a capacitor. If you charge a capacitor, the capacitor follows the law. Q is equal to Q0. Inside the bracket we have 1 minus t over RC. RC is the time constant. Okay, so I am writing right now a similar equation that if you start heating a sample, okay, the temperature will rise like this. Here tau is the t is the time and tau is the relaxation time or the time constant. Final temperature, if we substitute the value of t here to be infinity, then theoretically it attains the maximum value. For charging of a capacitor also, if t is equal to infinity, if we leave the capacitor for infinite time, then only we get the steady state or it is fully charged. But otherwise, if you wait for 4 or 5 times of time period, suppose time period is 1 second, you wait for 5 seconds, okay, the maximum charge on the plates of a capacitor is 1% less than the steady state value. It's around 90%. You can make out that calculation. So here also the same argument holds that for t is equal to 5 tau or 6 tau, 99% of the final value can be achieved. So if t is equal to 5 minutes, then the reading can be taken after 30 minutes. So this allows 5 readings in 3 hours. Okay. So if we argue on this, now let us find out the value of tau, because we have written this equation just on the basis of a capacitor. Here we are heating the sample. Okay, it is not a switch that you heat a sample, the sample attains 100 degrees centigrade. It will take some time. So it is going to follow a law like this. Let us see whether it really follows a law like this or not. So we write down the equation. M into S is the thermal capacity of the entire unit, which consists of aluminum cup, heater and the thermometer. d theta over dt, okay, d theta over dt is the rate at which the temperature increases as a function of time. This plus c theta here comes from Newton's law of cooling. Okay, in fact, Newton's law of cooling, if you write down, if the difference between the temperature of a body and the temperature of the surroundings is very small, okay, then we can write this to be equal to sigma a T1 plus theta to the power of 4 minus T1 to the power of 4. T1 is the temperature of the surroundings. T1 plus theta is the temperature of a body. If theta is very small, what we can do? We can pull out T1 to the power 4 from here. Okay. So finally inside the bracket we will be left with 1 plus theta over T1. Since theta is small, we can make use of the binomial theorem. So if you make use of the binomial theorem, we can approximate this Stephen's law as 4 epsilon sigma a t cube into theta. So this we call as c theta. So here this c theta here is, this one is the rate. This comes from Newton's law of radiation. So m into s into d theta over dt. This is the rate taken by these things. Okay, and c theta is the heat lost by radiation. This is equal to the total heat. So if you solve this equation, now you can see this equation, it is similar to the charging equation of a capacitor. Okay, so if you compare the two, then we can write down this as theta is equal to q over c, 1 minus e to the power minus c over ms into t. Q here is not the charge. Okay, q is basically the heat. C here is not the capacitance. C here is a constant. Okay, that was there on the next page, and this is the time constant. So if you compare the two, we can find out the value of tau to be equal to ms over c. Okay, so if we want to minimize the value of tau, thereby allowing our student to complete the experiment in lesser time, the value of m must be as small as possible, and that is the reason why a lightweight aluminum cup has been used. Okay, a lightweight cup for small time constants, we require mass m to be very small, and that is the reason why a small cup here has been used, or why the mass of a sample must be as small as possible. Okay, you can further calculate the value of sigma is known. Let us take epsilon to be 1. Suppose the temperature is 300 degree Kelvin. So we can, for T less than 300, Okay, the value of this must be equal to 5.8 gram. So you can make similar calculation while designing the mass of the sample that you make use of while determining the stiffness constant. So that is why we are using the small lightweight copper. So this is all about